Imagine your model is stuck at mediocre accuracy and you are facing an expensive decision. Should you spend weeks collecting and labeling more data, or is the model itself the real bottleneck? Those two paths cost very different amounts of time and money, and guessing wrong burns both. The good news is that there's a simple diagnostic plot that answers this question before you commit a single resource. And today we are walking through exactly how to read it. It is called the learning curve, and it quietly turns a costly gamble into a clear picture you can act on. So how do we actually read one of these curves? You plot two lines against the amount of training data, and the story lives in how they behave. Start by plotting two scores as the data set grows. One line is the training score, how well the model does on the data it learned from, and the other is the validation score, measured on held-out data through cross-validation. The horizontal axis is simply the number of training examples. Now, look at the first pattern. When both lines flatten out at a low score and sit close together, that is underfitting or high bias. The model is just too simple to capture the real pattern, so pouring in more data will not rescue it, because it is already plateaued. What you actually need here is a more powerful model or better features, not a bigger data set. Then there's the opposite pattern. When the training score stays high, but the validation score trails far below it, that wide gap between them is overfitting or high variance. The model is memorizing its training set rather than generalizing to new cases and options like regularization, a simpler model, or simply more data would all work to tighten that gap. Finally, watch the shape of the validation line itself. If it is still climbing at the right edge of the plot rather than leveling off, that rising slope is a direct signal that more data would keep improving the model. That is your green light to go collect it. Here is the shift the learning curve gives you in one honest comparison. Without it, you're basically guessing. Accuracy is disappointing, so you throw effort at whatever feels intuitive, maybe gathering thousands more examples, only to find weeks later that the model was too simple all along and the data never mattered. With the learning curve, you diagnose the situation from the trends before spending anything. The gap between training and validation, plus whether the curves are still moving, tells you whether you are underfitting or overfitting, and the answer points you straight at the right fix instead of an expensive guess you might regret. Let's distill this into 3 ideas worth holding on to. Plot the training and validation scores against dataset size. Watching both lines together, rather than a single final number, is what makes the whole diagnostic possible in the first place. Read the gap between the two lines. A small gap at a low score reveals bias, while a large gap with strong training but weak validation reveals variance. The distance between the curves is the diagnosis. Turn that reading into a decision. The curve tells you whether more data will actually help or whether you should change the model entirely, which saves you from a costly and often wrong guess. There is also a close cousin, the validation curve, that varies a hyperparameter instead of dataset size. All right, for takeaways worth keeping. A learning curve plots training and validation scores as the amount of training data grows, so you can watch how performance evolves. When both curves plateau low and close together, that signals underfitting, while a wide gap between high training and low validation signals overfitting. A validation curve still rising at the edge tells you more data would help, whereas a flat one tells you it would not. Used well, it turns an expensive guess into a clear decision about data versus model. For more machine learning ideas explain this simply, standarity.com is where they live. See you there.